Okay, we're recording now. So yeah, let's get started. Thank you, Carlos. So I'm gonna share my screen real quickly. So thank you everybody for joining. As I was mentioning, my name is Enrique Noriega. I'm a member of that lab, and today we're going to cover how to use LLMs to generate specialized SQL code using models that are fine-tuned for code generation. And I'd like to start by introducing the motivation, like why would we want to do this? If you're familiar with databases, you have definitely interacted using SQL code. So SQL stands for Structured Query Language, and it's a way to retrieve data out of tables that represent relations. So there's a theoretical concept called relational algebra, such that you can decompose in a specific way relationships between data and store them into tables. So a table would be a catalog, and we can split them together such that there's not a lot of redundancy. But a way to retrieve this, or the standard way to do this, is using SQL code. We're going to see some examples here, and this means that you need to have, excuse me, certain experience or knowledge. So you're assumed to have certain knowledge about basic to advanced SQL, depending on the structure of the database. So this is not a big deal. I mean, engineers do it, and there are DBAs and a lot of roles based on data that require you to be acquainted to it. But you might not necessarily be working such role. If you're a scientist and you are dealing with sharing data with our labs, or getting data sets that are distributed in a database format, you will need, there's no way going around it. So you'll need to learn an extra tool that might not be the core of your business, but you will actually need in order to retrieve the data. So that is where we can tap into large language models because they offer a powerful solution such that we can basically request them to look at the structure of the database and ask questions about the data. So these questions are going to be in natural language. It's going to be English or Spanish or whatever language you are comfortable with, as long as the LM understands it. And you can just ask it to translate that statement into an actionable SQL query. So this query might be simple, or it might be complicated, or it could be a sequence of queries. So in today's session, we're going to start walking through a ladder of examples that we go from, like, okay, basic proof of concepts. What can we do, or how can we command these LLMs to actually write a query into generating a plan to fetch the data to answer a complex question that is not easily answerable using a simple query. So this will allow us to streamline some of the workflows that we have, because we might not need to develop an app for it, or a script. It'll reduce the dependency of database specialists. I'm not trying to take the job out of anyone, but like, if you're not in the business or being a software developer, but you're a social scientist, you'd rather focus on answering the questions that you're investigating. And that's a great use case of generative AI tools. So they're here to help us navigate the data and solve tasks that required much more nuance before, but now they can be augmented. So we get an increase in our capabilities. Some examples of people who might benefit by this are scientists that are in the biomedical research field, or financiers, people doing business intelligence. But granted, if you're doing business intelligence, you probably good benefit of knowing SQL. But like, I know a little bit of SQL. I'm not an expert, but I prefer to get an LLM to do 80% of the job for me and then just tweak it as I see necessary. And basically, in any discipline where structured data holds any valuable insight, but there might be a barrier like between the data and myself or yourself, which can only be overcome if you are able to craft a complex query that joins multiple tables or has an inner query to answer another question or whatnot. So how is it possible that the LLMs can do this? Well, it's basically, I would say, a side effect of training the LLMs to write code, source code, like programming language code. Why is this? Because SQL is basically another programming language. But instead of writing Python code to, build an LLM-based application, or instead of writing JavaScript code to build a web app or an interactive or responsive website, you're interacting with a database management system. So the modern LLMs are trained on large-scale datasets, and among these datasets, there's a lot of SQL code. So, OpenAI, Meta, Microsoft, and whatnot, they have extensive repositories of SQL queries, and you can go on GitHub and find a lot of SQL code. There are many flavors of SQL, depending on what is the actual engine that you use. Could be MySQL, could be Oracle, SQLite, Postgres. All of them are similar, but they have their own flavors. It's like, you might be speaking English here in Arizona, but if you're on the East Coast, you're still going to be speaking English, but there's going to be another lingo or another accent. So it's the same, similar thing, but with small different flavors. Beyond that, some of the models have been explicitly fine-tuned to do this specifically. This could be GPT-4 or its successors, the Llama family of business, or Quencoder. So today we're going to use Quencoder. These are LMs that have been further fine-tuned on datasets containing natural language to SQL mappings. And this improves a lot of the accuracy. Why? Because you're showing them this is the input and this is the SQL out. This is the input in English or in Mandarin or whatever other language, and this is the output on as a SQL statement for this specific engine. So it could be MS SQL or it could be Oracle. Pick your favorite flavor. And we can also do some prompt engineering and include some examples. So examples are also known as few-shot learning, depending on who you speak with. And these are great because they help the LLM on generating more accurately and syntactically correct queries. So on today's presentation, we're going to make extensive use of this, and we're going to see how we can get better results if we provide structure within the prompt. So I have speaking for about 10 minutes, and I'm not trying to bury the lead. But if you want to get hands-on, I can give you the TLDR before moving into the actual code. So the TLDR is that you do not need to be an expert on SQL, although you need to have some specific familiarity on how SQL queries are constructed, such that you can articulate your question in a way that is more likely that the LM is going to get it right on the first prompt. This tool is great because it is able to give you complex relational algebra statements. So these are queries that contains joins or multiple joins or inner queries or unions, but they can be spelled out. So you can actually ask it as if you were speaking to another person, and the LM is going to articulate that request as the SQL statement. However, these are not a silver bullet. You're going to see how there are mistakes, but on the plus side, there's the industry is moving towards using a agent-based systems, which can self-correct. So what does this mean? It means that if an agent-based system that is using an LM to drive its flow figures out that it got it wrong, it is going to attempt it again, learning the lesson of failing on the prior step. So this might be a little bit abstract, but we're going to see a couple examples of this. So now that being said, I'm going to show you some. I put here notebook example, but this is going to be more like a repository example. So let me stop sharing my slides and I'll start sharing the code. Okay. So I'm going to make the font larger. And please, if someone on the audience can tell me if this font size is legible.
It looks good.
Thanks. Okay. So what do we need in order to test this? So we need database, right? So you obviously. So today we're going to use a database that I put myself together and that contains PubMed articles. So what is a PubMed article? Is medical research articles that are stored on the National Library of Medicine website that is called PubMed. So this is a great resource because it has millions, like literally it has millions of papers that span all the way back to the 18th century until today. Like today, some papers were submitted there. As long as we still have it, it's a great resource, and it's free, so you can download it and keep a copy for yourself, etc. Among those papers were like I didn't download it all and create a database out of that because it gives me terabytes of data. But one of the useful features is that they have an index. Let me see if we can. I should have the file somewhere here. Well, it doesn't really matter. So it has a CSV file, and that CSV file has the name of the paper and metadata, as if when was it published, who is the author, what is the journal that it came from. We also have the journals, which is what we're looking at here, and we have like the URL of the journal and the URL to the paper, such that we can actually take a look at it. So you can think of the data on the database as a giant table that was decomposed. And I created a toy database around it. So that toy database contains 3 separate tables. And if you're not familiar with this concept, please feel free to stop me and ask a question because it's so important that you understand the underlying data structure such that we can walk through the example. I'm using SQLite, which SQLite is a database that stores your data as a file instead of a server that you need to deploy somewhere. And it's convenient for smaller databases. So this database is going to have about 7 million records. And the central piece is the article entity. So I'm using SQL model, which is a wrapper on top of SQL Alchemy. And you can think about each class representing a table on the database. So this is also an example of an object relationship manager utility. And if you're in software development, it's a really useful tool because it allows you to interact with your data as if it was an object-oriented programming language instead of having to explicitly write those queries for yourself. Today, we're leveraging that such that we can have just a better look at what's the structure of the data. The central piece is the article table. As you can see, it has many fields. So it has an unique identifier. So this is just like, you can think about it as an index to each of the articles, where the first one starts with 0 and last one finishes with a number, which could be its index on the database. It has a path to the file name. So each paper is going to have an archive file, which contains, think about it as a zip file that contains the PDF, an XML files that has the same contents as a machine readable text file, It has the images and it has the the additional material. So the path is going to be the path to that archive file on the server that hosts this data. We have a PMCID and a PMID, which are two separate identifiers for on Puppet Central. So the important one is PMCID because this is it's a string that will allow us to fetch that paper by its key. It's platform independent, meaning that the PMCID is going to be the same here in our database as it is on Puppet servers. Whereas the ID that I'm showing you here is just its scope is only the local database that we hold. A PMID is similar, so consider them like a one-to-one mapping. We have when this article was last updated. We have a journal ID. A journal ID could be a foreign key. That means that this is a pointer to the other class that we have here, which is journal. The journal only has its name and a flag that tells us whether it's commercial. So the ID here should be equivalent to the ID in journal ID of article. Why do we do this? Because we don't have to keep multiple copies of the same name and same flag here. So that is just a concept of normalization databases. But for the sake of our demonstration, if we fetch an article, we can see directly its journal ID. But if we want to know the name of the article, we need to make one hop. So that is called a join in the database lingo. So the LM can figure out how to do that for ourselves using this structure that I'm showing you here. And we have stuff about when these articles were being published. So the year, the month, the day, what is the volume of the journal in which it was published, issue, and e-accession. It's also something similar, but like digitally, like what is the URL? And we also need to know the license. So it's a similar situation here. Could be Creative Commons, could be, I don't know, copyleft, Puppet is open access. So there are a few licenses. The identity of those are not relevant for the scope of today's demonstration, but we also need to decompose that. So we also have a flag, whereas a paper was retracted. You know, sometimes some papers might be retracted for various reasons, like the author, like, you know, plagiarized something and it was cut, or it turns out that there wasn't a mistake in the methodology and the results are not valid, or it was proven false otherwise. These papers, they're not deleted, they're just retracted. So we need to know that. So this is the central piece for our data model. These are ancillary classes or tables. That being said, how can we tell the LM, like, you know, this is the database, that the database is going to be a file, and this is the data model. So this is the structure of the data model. Look at it and tell me, like, I want to know how many articles were published today, or I want to know which articles were published in the prior decade on this specific list of journals. So I'm asking some questions about the data, and the LM is going to be responsible of creating a SQL statement by looking at this structure. And I want to show you two approaches today. The first one is the text to SQL one. And I'm just going to walk through the code, and we're going to run some examples out of it. But I think that the key insight of this is the system prompt. So on the system prompt, we condition the LM to adopt certain behavior. So today we're telling it that it has to behave as if it was a database engine that contains some tables and their schemas. The LM's task is to generate those SQL statements necessary to map the user's query. Sometimes the LMs get creative, like they're going to try to explain you why they did this. Today, we don't want that. We only want the SQL stuff. We have to specify that we want SQL for SQLite, because sometimes a query would look okay, but it's not going to be compatible with your engine. So it's important that it knows that our engine today is SQLite. And we don't want any preamble or explanation along that SQL statement. I'm going to cut this out because maybe we can provoke an error, and we will see how adding it back fixes it. So this is the first condition that we need to follow. We need to prime the LM to behave in a certain fashion. Then we need to pass the schema or the data model. So schemas, this is basically copying and pasting those source files into the system prompt. I'm not going to explain this again because I already did it, but it has all the same fields. I made a few changes. What is important here is that along the name of the field, which represents a column on a table, it's important that you specify what is the data type. Strings in SQL are called varchar. Int numbers are integers and whatnot. So it is also useful if you specify what is the description of each field. Sometimes it'll be evident by its name, but sometimes it can benefit if you elaborate a little bit more because you're hinting the LLM, what is this about? We did this for the same tables, for the other two tables, and we craft our system prompt. So that is probably the most important part of today's presentation. Then once we have the system prompt, we're going to use LangChain in order to create an LLM pipeline that is in charge of execute or of generating our SQL statement. So I'm not going to go into a lot of detail about how to do this, but there are a few other lectures or recordings on the Data Lab channels where we cover more extensively how LangChain works. But you can think about it as a pipeline where we put multiple sequential components. The first one is that we need a chat prompt template. So a chat prompt template is a template for the conversation. So a conversation, in this case, is going to be like almost bare bones. So we only have a system prompt, which we just defined. And then we add a user message. So the user message only says, this is my query in natural language. Then we add a placeholder for it. And then we add a preamble to what is the SQL statement. This is a template because we're not specifying what is the query. So by query here, I mentioned my ask in English. Instead, each time that we call it, we're going to substitute into this placeholder my input. So once we have that prompt template, we need an LLM. So if you're using LangChain and you're using something like AI Verde, you can use the chat OpenAI class, and you will need to specify the model name and some additional hyperparameters. So the only one that I consider important in this case is to set the temperature to 0. Why is this important? Because by setting it to 0, you're enforcing that the response that you get out of the LM is going to be consistent. It's going to be always the same, because otherwise it might give you a query. Sometimes that works, but the next time you run it, it'll give you a different query that might be functionally equivalent or might be wrong. So you don't want, like when you're developing software, you want to be all this stuff deterministic, such that you can troubleshoot it appropriately and then shoot yourself on the foot. If you were doing something else, like some creative work, maybe you can increase the temperature that will foster a diversity on the response, but that is out of the scope from today's session. So finally, we put together our pipeline or chain in which we first wire the prompt template to the LLM, and then we just capture what is the string output out of it. And I created a few entry points. The first one is the one that we use to generate the SQL code. So what we're going to do here is that we're going to grab that pipeline that we just defined above, and then we're going to substitute our input into the query field. So that renders this prompt template into an actual prompt, because it substitutes our ask into the query placeholder. So that is like, once we get there, like job completed, but we can do better. So we'll see. Then I created a small utility function that takes a SQL query. So I should probably have named this differently, because it is confusing. But in this function, execute query, I am expecting a SQL statement, and I'm going to print the result. So I'm going to actually hit the database and retrieve the data. So like, this is not really important. Like, we get the connection string, which is the path to this database file. But if this was Postgres or MySQL, then there could be like a server IP and the port and the user, whatnot. That is the connection string. And we create an engine, which is basically the connection manager. We connect to it, we execute that SQL statement, and then the result may contain 0 to more rows. We're just going to print them. So we just want to read the output. We're not doing anything else fancier. So this could be the actual executable part of this demonstration. And if we put both together, like, we can generate some SQL statement from our input question. Once we get that SQL statement, we can execute it and see what happens, right? So that could be the base use case. So well, let's see in action, right? So I'm going to make this a little bit bigger. And today I'm using UV. If you use Python excessively, I recommend you to take a look at it. It's a great tool. But it allows us to manage the dependencies. We can talk about it later on AI Makerspace if you're interested. But the important part here is that we want to specify the parameters, like what is the model, what's our API key. So we're going to use QuaintCoder, and I'm going to explain you why in a bit. Then we're going to run this function that is text to SQL. No, it's not .txt, it's .py. So what you see here that is missing a command. I'm using Typer to create a command line app out of it. So basically it gives us multiple entry points. And I also recommend you to look at it if you're developing Python professionally or extensively. But you can see that we got the generate SQL, or generate and execute the SQL, or execute the query. So these three elements or entry points represent these three functions that we have here. So what if I want to generate SQL, and let me make this wider so that it fits better. Tell me how many papers are in the data database. All right, so remember, we have a table called article, and a paper represents an article. So it's not exactly the same. However, the LLM was able to generate a pretty basic SQL query where it counts how many rows appear on the article table. So you may ask yourself, like, how did the LLM know that by paper I meant article? If we go back to the model file, sorry, no, to this text SQL file, and I scroll up just a little bit, you will see that nowhere did I specify paper. So how did it know it? Did it know that paper means article? Well, this comes out of the parametric memory of the LLM. So you that are in academia are familiar with this like a paper means article, like article is a more formal way to call a manuscript or a paper or whatnot. We don't have to specify it with the context that we've in system prompt. That is enough. And what if I want to actually know that specific number? So let's generate and execute it. So it's gonna give us the result. So on this toy database that I have, there are 6.5 million papers or entries on the article field. So this is pretty basic. So let's try to ask something different, like what is the year in which the first article was published? So let's see what we get out of this. Okay, so we're going to again to hit the article table, and we're going to look at the year column, and we're going to select which one is the minimum one. So let's see what happens if we execute this. So I see something chat. Okay, yes. Okay, so the first article that is available in this database was published in 1701. So you can see that it is pretty old. So let's see, what if I want to access it? Tell me the URL to access the first article that have the oldest publication date. I don't know if this is going to work because I haven't tried it. But okay, so if we inspect this, again, we're looking at article. You can see the response is a little bit more complex. We are looking at path, which is the path in the file. So here's the first mistake. I was asking for a URL. I was not asking for a path to the file. We'll see how to deal with this. But we're ordering this by the year, so in an ascending fashion, and then by the month in an ascending fashion, and then day in an ascending fashion. What does this mean? That we're going to take all the papers and like the ones that were published the earliest in the first year, are going to show first, and then we're going to do a second sort in which we'll look at the month and again on the day. So presumably this will give you the list of articles ordered by their publication date, and it's going to limit the search to the first result, which should be the earliest one. So what happens if we actually run this? Execute. So we get something here, like this is a path, but it's not a URL. So we're hitting a limit in how the current code, how it's configured, can work. As you can see, like the model, the development model that I have been following for this example, it's like a function. Like you give me a question in English, I want single SQL statement. I'm not asking it to do some reasoning above it. And that was specified here on the system prompt. Generate SQL statements necessary to resemble the user's query. So if I was clever enough, I could reconstruct the URL using the PMCID, but I'm not asking the LM to do that. I'm just limiting it such that you're going to generate SQL, nothing else. So we hit a constraint here. We'll see how to deal with that using an agent example, but let's finish up with this specific one. What if we want a something more complex? I want what is the unique different licenses were use. No, this without an H, right? I failed my English class. How many articles are published with each? Okay, so first let's dissect this result. We have Creative Commons, like the vanilla one. Then we have Creative Commons, and I don't know exactly what is this. So these are some variations.
Commercial.
Oh,
Non-commercial.
non-commercial, and then some sub variation nested
Non-distributable.
into. So here, like, in order for myself to get this, I will need to understand better the structure. But I didn't have to do it. So I asked for like a breaking down, like a pivot table on Excel or a spreadsheet. But I had the LM to do it for me. So how can we take a look at this query? We can use the same command line application and see what type of query do we get. So here, as I would expect, I want to know what is the license name, how many articles are available for each license. The pivot table that we're going to use is article, but we're going to join it with the license table. So this join, it's like probably the first step into intermediate SQL, because now you're putting together, or you're using the relational algebra to merge back the relations that were decomposed during normalization. And if this sounds foreign to you, it's because you don't really need to know it, like, because this is database stuff. It is not biologist stuff. It is not social scientist stuff. Like it's something that is useful to know, but you shouldn't actually know it unless you work a lot with it. So the LM helped me to figure out this. And then once I put them together, I grouped them by the license name. So basically, I grabbed each of the articles in the table and appended what was its license name out of the license table. Then once I had that blown up table, I grouped them by their article name, and then I just counted how many records were on each. So this is the first palpable useful result that I could attribute to using a methodology like this. But what if I ask for something even more complex? So let me see. What if I want to know the number of articles published each decade since no each yeah in the 20th century. Okay, so for the keen eye of you, can you spot the problem, like the immediate problem with this? So it is that we're getting this, like, what's this? Like, this is markdown code preamble. I didn't want to do that. I didn't ask for it because when I tried to execute this, it's going to crash, because this triple backtick followed by SQL is not SQL code. And you can see it here on the error message. So at the beginning of this talk, I was telling you that we don't want that. So you can specify it on the prompt. So you can do some prompt engineering to try to fix it. So let's see what happens if I ask again? Okay, so now I got a SQL query. Let's try to dissect it. But you can see how the complexity starts to increase. So there are some constraints that I put on the data request that are encoded as a part of the statement. So I asked for articles in the 20th century, and we're using between 1900 and 1999. So that seems to be correct. I mean, semantically, it is, because this is the 20th century, and we are generating on the fly a new field called decade, which takes year and divides it by 10. And I'm not sure, like, why is it doing, like, this cancels out, right? But like, it's still valid. But it uses it in order to create a criteria to group by. So let's see if this runs. Looks like it did. So in the first decade, what if we change this to since? You can see how this constraint changed, and this is still valid, but now we're including the 21st century. Okay, this is something I want to show. Like, on the eve of the 21st century, how research started to explode, basically. Like, the productivity, like you see on the first decade of the 21st century, it was by an order of magnitude more than in the prior decade, and how it has been increasing. Like, on the 2010s, it increased even more. On the 2020s, we already exceeded that from the prior decade, and we're just at the middle of the decade, right? So we're in 2025. We still have another 4.5 or almost 5 years to go. I don't know where this is going to stop. But this is a cool example of how we can leverage this tool. But what if we want to go even further? So let's see, the average yearly number of articles each decade since 1880. So I'm starting to ask for some statistics. Okay, gave me something. I'm not sure if the SQL statement looks correct. Okay, average articles. So you can see there's an inner query here. I have to say, I'm like pretty impressed with what getting out of it. Like, the last time I tried this, it failed, so I had to use the agent approach. But we still have 15 minutes, so let's see. Let's hold this thought and go into the agent-based tool. So I mentioned that sometimes the LM might make mistakes and will get crashes out of the execution engine. And we have to deal with that. So we need to inspect why did it crash? So we need to read the actual query on the LLM and try to prompt engineer our way out of that mistake. But that's not, like, what is the point of doing that? Like, we're supposed to be using AI, and it should be smart enough to correct itself. And I can tell you that it is, but we need to use it correctly. So with agent-based approaches, what we're doing is that instead of using a single function call, we have a loop. So a loop could be, I want to know this, and I need the answer. I don't know how many times, or I have these tools at my disposal. Just use them as many times as necessary, until I get an answer to this tool. But you're not hard coding that that behavior. You let the LLM drive itself until it reaches the desired output. So one way to do that is using small agents. Small agents is a Hugging Face tool to build code LLM-based agents. And we're going to factor out that pipeline as a tool. So we're going to use these classes provided by small agents and create a text-to-SQL tool. We're going to take that system prompt and add it to the description of the tool, and just specify that this takes a SQL query to retrieve it, and ask it, do your best to pass an efficient query that fetches only the information that you need. We don't want anymore. We specify what is the inputs and outputs of this tool, and we write the code. So based on the description, this tool is expecting a SQL statement. So I'm telling the LLM, like this text to SQL tool, it expects a SQL statement that conforms to this specific data model that contains the article table, it contains the journal table and license table, and I'm going to execute it, and I'm going to return you the actual output. So the only difference here is that instead of printing the return, I am returning the value that I got out of the database. And then the agent is going to take care of using it productively enough such that we can respond this. Now instead of AI Birdie, I'm using the Hugging Face Inference API. It still has the Quencoder, and I have been telling you a couple times that we're going to use Quencoder. Why? Because Quencoder is a model that was fine-tuned for code generation, and this agent is not a tool-based agent; it's a code-based agent. What do I mean? Let me show you. So I'm going to run this, and I'm going to show you another screen. So it needs just a moment to fire up, but it creates a web server. Let me open this in the browser, and I'm going to share my browser. So I'm going to stop sharing that. I'm going to start sharing Chrome again. So this is thanks to the Hugging Face folks that they built a gradual UI on top of it. But I'm going to ask it, I want the oldest paper that has a year. Hopefully this is better. No, I want to know which journal was published. And finally, I want a URL to on PubMed. So now I ask for three things at the same time. The agent system is able to figure it out itself, like decompose that into individual tasks and reason about it. So one of the nice things about this UI is that we can pick into what is the thought process of the LLM, because we are going to see it on our next session, how to use tools, and we're going to go into a little bit more detail on how this works. But it basically is tasked to think about how to solve it and to generate Python code to execute the steps necessary to solve them. So the thought is like, I need to solve this by decomposing the ask into three separate tasks: retrieve the oldest paper with a specified year from the database, identify the journal in which that paper was published, and find the URL on PubMed Central. Given that the database assume, okay. So we did provide that. So this is a mistake, but it'll be able to recover itself from it. So it is using the text to SQL tool. And yes, obviously, There's no table called papers. There's table called articles. Okay, so um, okay, articles. Okay, this is letting me down. Hold on. Let's go back to the code and try to recover this. Oh yes. Hold on. I'm not sharing the screen. Well, actually, yeah. Let's do something a little more clever. Let me go out on a limb to try to fix this ad hoc and see how we can leverage these agents. So I'm going to open this again. Use fetch the schema of the database using a SQL statement. Then use it to tell me which is the oldest paper with a publication date specified and generate a URL to open it in DMC. Uh-oh. I exceeded my quota. So hold on just a sec. We can fix this. Model. So I have 5 minutes. If I cannot fix it in 5 minutes, then I'll finish it on the next session. Okay, let's try this. Let me go back to the server. Asking for API base. Just give me a moment. So I needed to unshare this because I don't want the API key to leak into the recording. But I am almost there. Okay. Let me share my screen again. So this is the difference. Instead of using the Hugging Face API model, I'm using Little LM, and I'm trying to connect to AI Birdie. So let me see if this worked. No, it didn't work. Hold on. Okay, well, no, we're out of time. So I'm going to have to call a rain check and show this demo on the next session, which is 2 weeks from today, where we're going to cover tool use, and this is an example of that. So, but let me share back the slides. So the key insights of generating SQL using LLMs is that you need to specify the dialect ahead of time. That's SQLite. You need to tell the LM the schema if possible. You might get away with asking the LM to fetch the schema for yourself and use that on the next round using the agents-based approach. I wasn't able to show it today because I failed to pay for Hugging Face credits, but I'll show it to you next time. Be specific about the desired information that you want. So don't like go straight to the facts that you want to retrieve, because if you're ambiguous, you may get a result that's not what you were expecting. And using the agent-based approach, you can mitigate failures, but the agent's not as powerful to mitigate my failure today. But I'll come back stronger. So this is it for today. I think that you were able to get something valuable out of how to use LMs to get SQL. Harry, yes, you will get the code. I'll add the link to the repository on the website of the UA Data Lab, and we'll use this for next week's session. So next week, not next week because it's spring break, but in 2 weeks from today, we're going to be reviewing tool calling for LLMs, and it's closely related to the agents. So I'll start with this example and do something else besides calling SQL. And yeah, that's it. So questions?